So I'm going to
Excellent.
give you a talk today. Great to be with you, by the way, and I see a very eclectic group. So thanks for joining me. And I'm going to spend the next 45 minutes talking less about my own research and more about opportunity in this research field that I'm calling microendomicroscopy. That's unusual for me, but I relish the opportunity. So the sort of the strap line for this talk is seeing the small with the small, and hopefully you'll be very clear on that by the end. I'm coming to you from Guildford in the UK, just outside of the M25, sitting neatly between Heathrow and Gatwick, although that doesn't seem terribly relevant anymore. But with nearly 25 universities in the surrounds and a very significant proportion of UK's R&D, it's a vibrant environment and a great place to do research. I'm based at the University of Surrey, and again, I'm actually based in my lounge room most of the time, so place seems to be rapidly diminishing in terms of importance, but this is a picture of Stag Hill, where most of the university is. It also sits on the other side of the A3 in Manor Park, and it is a wonderful facility and location. I invite you to come and see it in the good times. I particularly like to acknowledge the members of the group. You can see that there are some new starters. We like to get them in young at Surrey, and especially Gavrielle Untracht, who you can see I'm pointing to with my mouse. Gav is finishing her PhD with me, and she's been instrumental in helping me put together some of the materials that I'm going to present to you in this talk today. So, what is a microendoscope? Well, that is a very small endoscope. What is an endomicroscope? That is an endoscope that functions as a microscope. And what is a microendomicroscope? Well, that is a very small endoscope that functions as a microscope. I want you to try to remember that. That's why I've put the extra hyphens in there. There will be a test at the end. You've got to be able to differentiate your microendoscopes from your endomicroscopes. So let me begin by asking how small is small in the context of medical imaging or microscopy in medical imaging. Let's just set the scene. So I like to start with this slide, which shows the state-of-the-art image of the human brain. It's a colleague's brain from the University of Queensland. Just let me adjust my screen settings there. And what you can see is, well, not very much, even though that is not clinically widely available at the moment. It's higher resolution than clinical standard. And then if I then consider what we can see in the mouse brain by comparison, this is now a thin slice of mouse brain seen under a microscope. It's a slide which is taken from the Paxonos and Watson Mouse Brain Atlas, so you can download this too. And if I zoom in on that, you can see that there is a lot of structure and features. And I can keep on zooming in to the point where you see that these dark blue nuclei sitting in these neuronal cells are about 10 microns in size. You can see that I can see a lot more. And so this comes back to this question, this fundamental question of, can we actually bridge that medical imaging microscopy gap with optics? Can we perform that type of optics that I've just shown you on the mouse brain in the best case scenario? Can we perform that on in an in vivo scenario on a human, albeit in the brain or elsewhere in the body? And we clearly have an opportunity with resolution, but we clearly have a challenge with range. And that's highlighted at the outset here, where we can achieve much better resolution with optics than we can with other medical imaging modalities, but we are going to struggle with exactly how to get there. And I'm going to emphasize that point a few times as I go through this talk. So for the purposes of this talk, I would like to define small as the size of a cell or less. And so I would want to be able to resolve the constituents of cells. Cells are full of lots of things, but the main things are the nucleus. And if you come down from the nucleus to smaller structures like the mitochondria, then at a resolution level of 2 micrometers, I can begin to just about pick those things out, although the mitochondria are generally of the order of a micron or so in dimension. So that's going to be challenging. So I'm setting 2 microns as a number that you can remember in your head. And so let's ask the question though, why do we need to see cells in the first place? Clearly in the MRI image I showed you, we couldn't see cells, and in lots of optical technologies you can't. Well, let's just remember what disease actually looks like. And I'll just pick out cancer, for example, and I'll start with melanoma. And what you can see is, as we go from left to right in this chart, you can see we go from the proliferation of these melanocytes, these brown ones, to this rather crazy looking invasive melanoma at the end. So what we see in that is that we see how cells change their architecture, their individual architecture, and their conformations and their configurations. And so cellular change is really important. Ultimately, that manifests in large-scale structural change, but there is this connection between what's happening at the cellular level, right at the beginning, with what eventually happens on a macroscopic level that we can all visualize when we go to the doctors. So early detection of disease depends on cells. That same story is reproduced across all forms of cancer. This just shows a normal breast duct, and this shows a metastatic carcinoma of the breast duct, ductal cell carcinoma. And so what you can see there is, again, this recurring theme of abnormality of cells and early detection of cells being critical. Cancers don't actually only contain cells, they also contain stromal arrangements, so structural tissues around the cells, as well as vascular arrangements, which again form signatures on the same scale as the cells, but form different signatures that highlight the tumor microenvironment. So what's the need for medical microscopy when it comes to seeing inside living humans? Well, it's to see cells and their microarchitecture in real time, partly for the discovery and new knowledge that will bring, but also to guide on-the-spot medical decisions anywhere in the body, whether they be through biopsy guidance, they be through surgery, or they be through just diagnosis. So what's our wish list to do that? Well, first of all, we'd like not to remove any tissue in order to be able to do that. We prefer not to have to use labeling technologies, but that's a preference, not an absolute requirement. And we think we'd like to go arbitrarily to any location in the body. But I'm adding this extra layer of requirement here, and that is that we want to resolve cells and their constituents. Okay, so we need to resolve cells. You've accepted that. You're a very compliant audience. Thank you very much. We do that with microscopes. What's the problem? Well, the first problem is it's actually very hard to see cells at more than about 250 microns beneath the tissue surface. So why is that? Well, it's not because light doesn't go through things. Actually, light goes through things really well, as this slide shows. And indeed, it's not. There isn't any fundamental limitation set by absorption and scattering in the tissue. There is this lovely window in which we can penetrate multiple centimeters if we could potentially form the image. But forming the image is very, very difficult. This is actually a set of lines. It's a 300 line per millimeter grid. And on the right-hand side, there are 1 micron microspheres sitting on it. And you can see you can still see the grid underneath those little microspheres. But on the left-hand side, there are biological cells that have exactly the same scattering strength as the microspheres when averaged over that image size. And what you can see is that you can't see the lines very well at all through only a small amount of cells. And so that presents us with a big challenge. How do we get around that challenge? Well, let me first of all point out what the problem is, and that is that the wavefronts of that image are being aberrated. So when you try to do conventional transmission microscopy or reflection microscopy on such a simple substrate, you can't see anything very well, even on the scale of a few to a few tens of micrometers in depth. So how do we get around that challenge? Well, we get around it with optical depth sectioning methods. What these are methods that pick out a particular depth. And let's just quickly recap on the majority, the main ones. We can use polarization, although that's not commonly used, but it can be used as a discriminant. We can also more conventionally use confocal microscopy, the confocality of the location in the sample with the pinhole. We can use the coherence as a gate through essentially very wide bandwidths that produce low coherence, and so a very narrow gate. Or we can use nonlinear effects such as multi-photon generation or harmonic generation, which essentially have a dependence on a higher order power of the intensity and thus create a natural self-gating effect. And if we do those things, then we actually, in animals, in living animals, then we can produce some exquisite images. And this, in fact, is a field known as intravital microscopy. It specializes in being able to take these sorts of sequences in time, being able to reproduce these types of measurements. But you can see just at a glance, all the wonderful colorful images here, you can see individual cells in many situations in many parts of this mouse. Now, what you have to realize though is that this image is being taken through a so-called window model. So it's quite an invasive process to install this window in the mouse and be able to then record these images. Certainly we can record them at better than 2 microns resolution. That's great. We can penetrate shallowly or up to maybe a few hundred microns, depending on the method that we're using. And these methods most definitely have their place. It's a field in its own right. But there is another way, and that is through the microendoscope. Usually multi-photon microscopy, but not exclusively. You can see what it consists of here. Essentially, we take a grin lens of the type shown here. They can be multi-element or singular element. This one here is about 500 micrometers in diameter. You can put it into the object, and at the bottom of that, at some depth, you can capture that image. You can penetrate with multi-photon microscopy well beyond the end of the probe, possibly to 600 or 700 microns, possibly even further at the very edges of the capability. And that means that you can then do time-lapse imaging. This thing has a whole microscope behind it. This is a conventional objective, and above it sits the whole microscope. And actually, it isn't as small as it seems. This is about 500 micrometers, but these tubes are still of the order of millimeter scale, because these probes have to go inside those tubes to be able to perform this imaging repeatedly. Now, that capability has existed for the last decade or so. And it's able to produce really rather beautiful images. These are just examples from that same Nature Medicine paper from the Schnitzer group. And you can see here that there are exquisite tracks that you are captured on day 41 to day 61. And you can see that those are actually captured with very high resolution. The scale bar in this panel at the bottom of D here is 5 micrometers. So impressive results. So to summarize, intravital microscopy is a field in its own right. So how about that equivalent field in medical microscopy, imaging at the cellular scale in living humans? How well are we doing there? Well, let me first of all show you what you can do without staining any tissues. You know, I showed you the colorful images of the mouse. Those were all involving fluorophores. Here are unstained images of human breast tissue that has been merely put under a window. You can see at the right here that there is actually a very large lens, but you can see the sample chamber in the middle there. But you can see cells in these images, and breast tissue is very scattering. And so they're unstained. That's very nice. And if you actually look at a less scattering tissue, something like the human cornea, this is it in cross section, and these are on fast sections, so XY sections taken at various depths, you can see exquisite cellular architecture. So the fact that it's unstained is a big plus. It's simplicity. But we have to remember this is still a microscope. So it's not really achieving our end goal. But it's also interesting to remember that actually, if you can see into the body, you can see quite a long way. And microscopy can be achieved using a technology like optical coherence tomography in the human retina, which is more than 20 millimeters beneath the surface of your cornea. And in fact, it's rather transparent organ itself, but you can see individual rods and cones in images, and you can see the vasculature deep beyond the superficial layers of the retina, although you have to remember that humans are one of these strange beasts that actually have opaque objects in front of their visual receptors. We put the vasculature on top, so we're looking through it. Clever us. But nonetheless, it's a fascinating insight into what you can do if you can see into the body. You can do something similar with skin, but penetrate much less deeply. You see the deepest image here is 120 micrometers. We begin by seeing cells, and we end up by seeing the connective tissues that are primarily collagen in this instance. You can see, take that even one step further, that again, with a full microscope, carefully connected to a living human, you're even able to detect the dendritic cells that are taking place in a malignant melanoma. That's an exquisite image. It was recorded quite a long time ago now, but it demonstrates what you can do when looking from the outside with something very large and state-of-the-art. So we're still, however, only able to access relatively superficial layers at places that we can get to. But we can actually do that in endoscopy as well. And so I'd just like to show you an image of doing that. This is human in vivo imaging of the colonic mucosa. So it's in your gastrointestinal tract. And you can see these crypts, these flower structures that you can see successively being scanned as we move through the tissue. And eventually you can also see vasculature. Let me play that once more because I love it so much. And this is 500 micrometers by 500 micrometers. So you really are getting cellular resolution here. So it's a fantastic achievement. This instrument was commercial, but it's no longer commercial. Therein lies a story for another day. And OptiScan is a company that originated and I think is still operating in Melbourne. But the issue there was that this is actually a rather large endoscope. Even the confocal imaging window, I think, is about 6.5 millimeters in diameter. So that whole endoscope is closer to 15 millimeters in diameter. It's a very large object. You can do that with much, much smaller instruments, and they have been pioneered by Mauna Kea Technologies, whose Cell Visio suite essentially uses flexible confocal microscopy through fiber bundles, and have explored similar range of applications in the gastrointestinal tract. But they've also gone well beyond the GI tract to look at all of these other indications. Now, again, my purpose is not to go through these indications one by one, but just to give you a sense that actually they can look at quite a lot of different things. And let's look at how they can look at them. First of all, if we look at their operating channel diameter, the diameters are typically more than 1 millimeter, up to 3 millimeters, and the resolutions are at best 1 micron, more typically 3.5, and they are looking very close to the end of the probe, 52 to 90 microns, I think. 70 microns is the deepest I can see there. So we can get deep in the body with fluorescence endomicroscopy. We're mainly still looking at surface images, maybe a maximum 100 microns from the endoscope. Can't do any scanning in depth in the Mauna Kea technology solution. We can resolve in the 1 to 3.5 micron range. We need to use a label, which I haven't pointed out before, and most probes are more than 1 millimeter in size. So let's just remind ourselves of what I would like to set the future technology goal for microendomicroscopy to be. And that is cellular and subcellular resolution, so better than 2 microns, anywhere in the body, as far from the probe as we can get. And I want it to be small because it's minimally invasive and able to get to places without perturbing things. So I'm going to set my maximum diameter at 500 micrometers. I'd like to have dimensions of less than 0.5 millimeter. Okay, right, take a deep breath. I'm just going to take a slight detour to ask the question, what about optical technologies that can see very deeply through tissue, you know, at the sort of 1 to 10 centimeter range and still be able to see cells? Now, we know that there are diffuse optical technologies, there are photoacoustic technologies that can see at the centimeter level now. 10 centimeters is probably stretching it. But certainly not without seeing the constituents of tissue. Now, again, I emphasize the fact that absorption does not set the limit here. We can know for X-ray imaging, for optical imaging, and for magnetic resonance imaging at RF frequencies, we have sufficiently low attenuation for that not to be a problem. So this is what we would like to be able to do. We'd like to be able to take our beam, which has gotten horribly scattered and smeared in the biological tissue, and somehow reconfigure it. If we knew the deterministic pathways that the light had taken, we can do that to actually refocus it to a point instead of watching it simply diffuse through the tissue. That is a wonderful holy grail. Of course, we need to be able to do that going there and potentially coming back, depending on the type of imaging that we're doing, but not always. But we need to be able to do it at least in one direction to be able to probe particular places in a biological sample. Well, this is actually the subject of quite a busy field, and you can see here just a whole lot of examples of experiments that were conducted in the 2010 to 2015 period, but many of them involve either adaptive optics, so correcting those wavefront aberrations through adaptive optics, or correcting them through the measurement of the transmission matrix of the imaging system itself, so measuring the transmission matrix of the medium through which the light is propagating. I think it's a really exciting prospect, and I think in general, as a generally applicable technology to get us to multiple centimeters, it's still a very long way off. But I'm going to show you in a moment where progress has been made on a much smaller scale, but nonetheless based upon very similar principles. But I'm going to do that as part of a general conversation around microendomicroscopy technologies. So let's just recap that it's possible to build these microendoscopic technologies through things of the type that I've shown here. Single mode fiber, just a cylindrical beam expansion segment, graded index, so that is a refractive index which looks like more or less like a parabola, so it functions as a lens, some form of reflecting technology, and we can build all of these things into a single monolithic substrate, and we can do that in all sorts of different configurations. We can build those into hypodermic needle-based systems of various sorts, and I spent a good deal of my time doing this a little while ago. And we can build them down to very small sizes. So this one is 30 gauge. That only has means it's 0.31 millimeters in diameter, and we can drill very small holes to extract the optical beam from the side. We can encapsulate to have total internal reflection, low loss mirrors, and we can put it into things like optical coherence tomography systems and get it to do very nice imaging. Now, you might think, oh, he's cracked the problem, he's imaging cells, but I'm not. It's a cucumber. The hole in the middle is 640 microns. So I'm imaging compartments in a much bigger structure. It works as well as any other OCT system, but it still can't see cells. That is emphasized in putting that type of technology to work. Again, this I think is a very interesting slide which highlights the problem. Again, some work that was done some time ago, enabling us to tell the difference between tumor and not tumor in a biological, in a breast cancer sample, and doing it via imaging freshly excised tissue, as shown here. When you then do the hematoxylin and eosin stained histology, you recognize that you've got very good match there. But the challenge is that there are many circumstances where actually this dense tissue on the left here is not simply tumor. It might be benign, it might be, but it's still dense tissue, it's stromal tissue. And you can't tell the difference without being able to see the cellular arrangement, the difference between tumor and not tumor. Now you can actually gain some further contrast through optical methods to do that. And this just shows one possible example of that. We used polarisation-sensitive OCT to measure the local birefringence. And that then gave us a measurement of the local order of the collagen structures. And tumours tend to disrupt that local order, so they reduce the birefringence. And you can see some very nice correlation between the tumour that's shown in these images at the right, highlighted, and the structures which you can see in the images in the middle panel, and the fact that you can't see those structures in the straight OCT panels themselves. Let me take a momentary sip. So I hope you're all still out there because I can't see you. So I shall crack on. So that's very interesting, but again, you can't really see cells in those structures, but you have got the potential to exploit a sub-resolution contrast to be able to tell the difference between tumor and stroma, which is the important element there. So it's nice, but in those measurements, we don't have anything close to 2 micrometers resolution. We do have, in some instances, a very small outer diameter, and we can penetrate deeply because it's a needle. It means we can push it into the tissue tens of millimeters. So this represents more or less the state of the art in OCT microendomicroscopes. These are just 3 examples, one very recent from this year, in which this beautiful hypodermic needle structure was created within a plastic sheath to image within the brain. You can see at its heart, it is a very similar structure. It uses actually a spherical lens at the end of the structure, polished to some point to enable the beam to reflect sideways. And then it uses a rotating system. So at the end of this little tiny connector that you probably can't see very well, it has a rotating joint. And then it's able to be put into this mouse brain. These are actually images of attenuation, but you still can't really see cells. The length scales upon which these images are taken are too coarse for that. The probes themselves are very small. You can see a multimode fiber there, and you can see, therefore, that you may be looking at maximum half a millimeter in diameter. And you can see nice matches with histology, but again, you can't see individual cells in any of those images, in any of those cases. Nonetheless, they do have superior resolution than was previously available, and they are pushing the boundaries, and that is, so all of that work is very commendable. However, we have to keep going. So a few years ago, we explored then keeping going to the next level down in resolution, and I wanted to show you this. This is actually a confocal microscope in a needle, and this we took advantage of some of our graded index fiber-based technology to create these little probes, and you can see a picture of it here. So this is actually the needle shaft at 720 microns in diameter. The optics are 350 micron diameter graded index, multi-element, so it's got a stronger focusing element at the end here, and as I say, scanned via simple XY actuation at the proximal end. And so this is when that needle was placed into a muscle sample, otherwise known as steak, and you can see then what we were able to deduce. And you can actually see individual muscle fibers. So this is a muscle fiber, and you can see these striations across it. If we just look to see how well resolved they are, they're resolved pretty well. Just remember that muscles comprise of ever smaller working units down to the so-called sarcomeres, which contain these bands. And so what you're seeing here is the evidence of sarcomeres in the muscle, which means that you're actually resolving at about the level of 0.7 microns in the lateral dimension. So that's quite impressive performance. And again, you're doing that 15 millimeters into the tissue, which you can't do via any other means. Now, this work was taken to another level and by a group that had been developing similar technologies for a number of years. And I just wanted to show you this because I think it's an absolutely exquisite example. This is a wearable endomicroscope, and you can see the microscope here. And here is what it connects to, which is a large platform, of course. This is what it looks like inside, and the beam comes in through here. There is a MEMS mirror arrangement. This is all scanning here, and eventually it ends up in a little needle which can be pushed 19 millimeters into the tissue. And at the same time, it can incorporate electrical stimulation. So this is the optical beam path for that, again through aspheric lenses, MEMS mirror, scan lens, tube lens, and off into the relay micro lens, and eventually hitting a prism at the bottom and being hitting the tissue in the orthogonal direction. And you can look through those papers and see endless, very high contrast sarcomere images. This is taken with second harmonic generation, so there is no dye needed. This is all exquisite, and in fact showing how the muscle responded, the sarcomeres responded to electrical stimulation. So, you know, I regard this as really a fantastic experiment. Another fantastic experiment that I wanted to share with you is based upon lensless multimode scanning. Two groups published similar results within a fortnight of each other in late 2018. And they essentially managed to take a piece of multimode fiber and use the transmission matrix method to be able to use it as an endoscope. It is very much a micro endoscope, and it's borderline micro endomicroscope. You can see that it's very small compared to equivalent 600 micron rod lens or a micro objective. And this is a cartoon of a mouse brain. And indeed, you can see that when they pushed the multimode fiber through the brain tissue in two locations, the amount of damage done was relatively minor. And I think that therein highlights the opportunity for very small footprint imaging devices, and that is that they do very small damage and they are able to then capture information about their surroundings, which in a way in which has not modified the surroundings itself. Now, in that imaging, they were able to demonstrate comparable neuronal imaging with comparable with confocal microscopy. That is quite a step forwards. It's a very small amount of multimode fiber. There is still a great big microscope behind it. Nonetheless, it's an outstanding experiment. It achieved 1.3 micron lateral and 20 micron axial resolution. It was only 125 microns in outer diameter. It was embedded millimeters into the mouse brain. It has a field of view which is equal to the core diameter of the multimode fiber. But it was even able to refocus computationally across 100 micron axial range. So an outstanding piece of work. But as you can see, not quite yet able to be taken to the field. So overall, I would say microendomicroscopy is in its infancy. And there is much new photonics needed to advance it, and much energy and good engineering needed as well. We would like these instruments to be deployable beyond the lab, certainly in a clinical environment and maybe in a wearable or an implantable environment, but most certainly in a miniaturized form compared to what is currently available. So in the last few minutes of this talk, I'm going to show you what currently exists and what we might like to focus on looking towards the future. And so we have some imaging system of the types of examples that I've shown you. We have some generic probe here. This generic probe is comprised of scanning systems, either a proximal scanner or a distal scanner, and some lens system and some focusing system. So all of these elements are key, and I've just listed possible examples of some of them here. So if we just focus first of all on the scanning systems, you know, these scanning systems have to scan in particular ways depending on exactly what application and how you've defined the system. But they also need to be able to enable scanning in depth as well as laterally. This is very much, the future is about volumetric imaging. It's about three-dimensional imaging. At the moment, all distal scanning technologies are much too big. They're all huge. Proximal scanners, you can relax the size constraints because in principle these are on the outside of the imaging system, but if they're only 20 millimeters away from the imaging system, size still matters. And the current gold standard in scanning technology, galvanometer mirror scanners, are exceptionally old technology, but we really haven't seen much come along to replace them. Very limited new options. These are some of the sorts of things that we might like to see. Fiber tip-based devices, liquid crystal or acousto-optic tunable devices, tunable structures in general, like shape memory alloys or piezoelectric benders. And all of those would be very welcome. And I think they're starting to be work in this area, and I'll show you in the next slide some of that work, but not so much about scanners, very much about the other devices. There are emerging micro lens technologies, and you will no doubt be aware of some of them. There's just an array shown here. We begin with a Fresnel lens on a fiber tip. We also have a metal lens on a photonic crystal fiber. And then we have the 3D printing based on the two photon polymeric technology. That work was really spectacular. More recently, we have development of guides that potentially can replace grin rods. That's Mikhail Lipson's group. And we also here have just an example. This isn't an imaging device, but it's an example of something which is complicated. So here we have in orange some prisms to reflect the beam sideways. We have a tapered waveguide in red, and we have a micro ring resonator in purple, just showing the sorts of things that the levels of complexity that can be achieved. But we need much, much more of this. This is really just scratching the surface. Most of these devices are not yet able to be deployed into systems and therefore not able to perform full-scale imaging, which is what we need. So how are we going then, overall? I think it's fair to say that the technology remains very much at the hero stage. We are able to get sub 2 micron resolution with sub 500 micron diameter probes, restricted very much to the animal regime so far. We haven't been able to take that any further at this stage, but we can, with a single company, be able to look at applications at the 1 millimeter level, albeit with fiber bundles that are limited in their capacity to resolve and not able to do full three-dimensional imaging. Nonetheless, I would put Mauna Kea Technologies in the hero stage when it comes to the advancement of technology at the commercial level. I think if we can achieve low invasion with technologies as small as multi-mode fibers, with a small footprint, imaging footprint overall, and retain that sub 2 micron resolution, will drive many, many new applications, and that represents genuinely exciting prospects. So I think there are opportunities for contemporary photonic devices, especially devices that incorporate optical fibers. I think there's opportunity for scanners, lenses. There is opportunity for optical fibers as well, and I haven't spoken about that today, but I think that's an area where, in particular, there are great opportunities in alternate spectroscopies, and in particular, Raman spectroscopy is really crying out for high-resolution imaging with small footprints, as I've described here. Now, I won't pretend to speak on behalf of Nick Stone, who I think is still to come, who is an expert in Raman spectroscopy. So with that, let me conclude by saying, again, the future is bright. There are a lot of opportunities in this area, and I commend you to giving it some thought as you develop your photonics technologies. The future is but that we can imagine. Thank you very much. Well, I think the thing is, you've really got to believe in what you're doing. Your work has to have a heart. You know, you have to be able to understand where it might end up. It doesn't mean you have to connect, you know, in a linear fashion from where you start to where you end. But you need, in this day and age, you need to move beyond the notion that it's going to be novel. You know, you need to be able to see the bigger purpose for what you're doing and really believe in that purpose and really then go after it. And only in that way, I think, are you able to really see that difference be made. And then I would say, you know, be connected, be open, work with people. Don't be protective of your ideas, but be professional and open with your ideas and share them with others. Have high expectations of others, that they also display the same honesty and integrity that you're displaying, and make sure that you then complement your skills with the skills of others. I think team working is absolutely critical. It is so productive and so enjoyable and so much more efficient than trying to become an expert on everything, particularly in these areas. You know, the areas I've described require so many different skills to engineer those systems and then to apply those systems. You've got to put together teams. So show the leadership to start putting together teams, bring people together, and enable them to reach their potential. I think that's as important as reaching within yourself to challenge yourself.